Hi, this is Ms. Cho, and in this video, we'll use the quadratic formula to solve quadratic equations and use the discriminant to determine what kinds of solutions to expect. We've looked at two other methods to solve quadratic equations, factoring and completing the square. But the thing is, not all equations are factorable, and sometimes when you complete the square, you end up with lots of fractions that you have to multiply and add, and it gets really messy. With the quadratic formula, all you have to do is plug everything in, and then it spits out your answer. Let's take a look. The quadratic formula tells us that our solution x is equal to negative b plus or minus the square root of b squared minus 4ac over 2a. What are a, b, and c? They're your coefficients when your equation is ax squared plus bx plus c is equal to 0. You must set your equation equal to 0. If you don't, you will end up with the wrong a, b, and c, and you will get the wrong answer. The second thing to know about the quadratic formula is this part under the square root, the b squared minus 4ac, is called the discriminant. The sign of the discriminant tells you how many solutions you have and what kind they will be. Let's take a look. Since the discriminant is b squared minus 4ac and it sits under the square root, when it is positive, you're taking the square root of a positive number and you get two real solutions because you get a plus or minus. That means your graphs look something like this or like this, where your parabola intersects the x-axis at two different points. When your discriminant is 0, you're taking the square root of 0, and there's no plus or minus 0, it's just 0. So there's one solution, and it is real, and it means your graph looks something like this, where it just touches right at one point. When your discriminant is negative, it means you're taking the square root of a negative number. That means you have two imaginary solutions, and your graph looks something like this, where it just floats above or below, and it never touches the x-axis. Let's take a look at how to use this discriminant in a problem. In our first example, we're asked to use a discriminant to describe the solutions of 3x squared plus 10x plus 5 is equal to negative 8x squared. We are asked to find how many solutions and what kinds. In order to plug into our discriminant, b squared minus 4ac, I first have to make one side equal to 0. That means I'm going to add 8x squared to each side, which gives me 5x squared plus 10x plus 5 is equal to 0. Now my a is 5, my b is 10, and my c is 5. When I plug everything in, b squared minus 4ac is 10 squared minus 4 times 5 times 5, or 100 minus 100, so this is 0. And when my discriminant is 0, that tells me I have one real solution, and I expect my graph to look something like this. I can verify this on Desmos by plugging in this equation, and I find that our graph does touch the x-axis just at one point, just like we predicted. Let's take a look at a second example. In our second example, we're asked to use a quadratic formula to solve 9x squared minus 11 is equal to 6x. The first thing I have to do is make sure one side is equal to 0, so I'm going to subtract the 6x from each side, leaving me 9x squared minus 6x minus 11 is equal to 0. Now my a is 9, my b is negative 6, and my c is negative 11. I'm going to recopy the quadratic formula so I know what to plug in where. When I plug in, my x is negative, which comes with the formula. My b is negative 6, plus or minus the square root of negative 6 squared minus 4 times 9 times negative 11 over 2 times 9. This is simplified is 6 plus or minus the square root of 36 plus 396 over 18, which is 6 plus or minus the square root of 432 over 18. I can rewrite the square root of 432 as the square root of 16 times the square root of 27, and I see another perfect square in my 27, and that's 9 times 3. When I simplify this further, my square root of 16 is 4, my square root of 9 is 3, and I'm left with 12 times the square root of 3. So I'm going to recopy that here. And I notice that all my terms are divisible by 6. So when I divide everything by 6, I have 1 plus or minus 2 root 3 over 3, which is my final answer. If I put this in the calculator, I find that x is approximately equal to 1.488, and x is equal to negative 0.821. I can verify this on Desmos by graphing. And when I graph, I find that I have two real zeros at the same points that I predicted using my formula, so I know that I'm right. Let's try a third example. In this example, we're asked to use a quadratic formula to solve 8x squared plus 6x is equal to negative 5. Again, I have to make sure that one side is equal to 0, so I'm going to add the 5 to both sides. Now I can see that my A is 8, my B is 6, and my C is 5. I'm going to recopy the quadratic formula so I can plug everything in. My x is equal to negative b is 6 plus or minus the square root of 6 squared minus 4 times 8 times 5, all over 2 times 8. This is negative 6 plus or minus the square root of 36 minus 160 over 16. This gives me negative 6 plus or minus the square root of negative 124 over 16. I can rewrite the square root of negative 124 as the square root of negative 4 times the square root of 31. And when I simplify, the square root of negative 4 is 2i, and my 31 stays under the radical. This becomes negative 6 plus or minus 2i root 3 over 16. And since all my terms are even, I'm going to divide by 2, which gives me negative 3 plus or minus I root 31 over 8. And this is my final answer. From the I expect to see a graph that does not touch the x-axis, and I will verify on Desmos. And when I type in my equation, I do have a parabola that does not touch the x-axis, just as we predicted. To summarize, the quadratic formula tells us that our solution is negative b plus or minus the square root of b squared minus 4ac all over 2a. This part under the square root is called the discriminant, and it tells you how many and what kinds of solutions you have. When it is positive, there are 2 real solutions. When it is 0, there is 1 real solution. And when it is negative, you have 2 imaginary solutions.